Anyway, example 1, free body diagram. Thomas, you said you wanted to draw the board? Go do it. We have an object sitting at rest on an incline. We need to show all forces acting on the object. Yeah. Go ahead and label it as F sub G. There we go. Okay. Nice. A few? Let's see what else Thomas has first. So we got something. Looks like something up there. Yeah. No need to label that because you're probably going to erase it. The errors you can see, right? Yeah, a little bit. Sure. Yeah. Yeah. That's it. That's all he's got. All right. First of all, free body diagram. Grab a seat. Thank you. I appreciate the effort. Free body diagrams, the way we draw them is we have a point to represent the object, and then from that point you draw in any forces that may be there. Does that make sense? All right, so a free body diagram does not look, yeah, we don't draw area distance like that. A couple guys going up. So let's start there. I like exactly one of his forces, and that's gravity going straight down. Clark, you said you have one? Something to add to it? I was going to draw it. You're going to friction going upward. I mean, I assume this is a car or something going down. Can I assume that? Yeah, except the fact that it says at rest right there. So it's not going down, it's just sitting on the incline. So it doesn't really matter if it's, yeah, you got to put that marker down. All right, so I like the fact that you said friction. Yeah. Which way is friction going to? Up the incline? I like it, that's perfect. So add on to the, no, not there, free body diagram. So on the free body diagram, blue, perfect. Start there, yep, and go up the incline. Yeah, okay, that's fair enough. Yeah, 1 point of contact. Perfect. Label it as F of F for friction. We're getting there. We're going to ignore air resistance for the time being. Since the object's not moving, right, since there is no air resistance, if the wind will blow real hard, I guess we would have another force. We're going to ignore that. One more force. The weight, yeah, that's SOG. Weight is gravity. If I were to add these two vectors together right now, it would be going this way, right? If the object's at rest, don't we have a force that pushes in that direction? You cancel that out? What's that called? Counter force? No. We said it in calculus the other day. It starts with an N. And negative normal force. Normal force, yeah. The normal force. Good. We have a normal force moving in that direction. Holy cow. All right. So we have gravity pulling straight down. force due to friction. Obviously, this object wants to slide down the incline. If it is not, friction is holding it in place. And then we always have a contact force called the normal force that's perpendicular to the surface. All right, we'll talk about objects like that a lot more. Example 2, and again, you will get a handout that has all of the examples on it. So maybe if you're taking notes, I would simply write example 2 and then show the work. And then you'll have a handout that you can refer back to the problem. That way you don't have to write down all the problem. So example 2, saying we have a 155 kilogram airplane. It's experiencing a force of 285 newtons to the west as a result of bending. At the same time, it experiences a 97.5 newton force that moves south. What is the net force? Maybe even before that, we should draw a free body diagram. Since we did so well with free body diagrams like the last one. This time you can draw the wind in, Thomas, but not restricted on it. So if we're drawing the free body diagram, what kinds of forces do we have acting on this object? Gravity. Gravity's pulling straight down. Since we already have west and south, we're not going to show. We're not going to draw gravity. Why not? It is flying. There's something that's canceling out the gravity, right? So it's not coming down. It's not going up. Isn't the lift and the gravity are going to be equal in this case? We have a force of 285 newtons to the west. And we have a force of 97.5 newtons to the south. So if we were to draw the free body diagram, it would look like that. In order to find the net force, now we're adding them. All right, we could do it graphically. We could measure out 285 centimeters or millimeters or something, 97.5, line it up, measure how far that is, measure the angle. All right, it's much easier to do it algebraically, especially once we have more than one vector and they're not all due north or southeast. All right, so in this case, we want 285 to go this way. And then remember, we add vectors tip to tail. All right, free body diagram, it looks like that. But if we're adding them, we add them tip to tail. So 285, 97.5. The resultant should be right here. How do we find that size? The Pythagorean theorem would give us the magnitude. Go ahead and find that. How do we get the direction? Remember, vector, force. Yeah, you're going to need the angle. All right, so to get the side, 285 squared plus 97.5 squared. Square root of that would give us the hypotenuse. And we said last time, generally speaking, we want how many significant digits? 2 to 4, yeah, so 3 would probably be appropriate. 301 newtons. Force is a vector, therefore we need a direction as well. How would I get that angle right? Not inverse sine. Yeah, if I want that angle, I would say the tangent of theta is opposite over adjacent. Therefore, we want inverse tangent of that. Make sure you're in degree mode. Can I do what? No, there are no programs. Again, 3 significant digits would be good. 18.9 degrees. 18.9 degrees is not enough. Yeah, you need to say 18.9 degrees in which direction. There are several ways to state it. Usually, notice we started west and we went south by 19 degrees. So I would say south of west. You might see it written as west and then 18.9 degrees south. It'll be the same thing. Start west and go 18.9 degrees south. Or you might see it written as, let's see, what would that be? 190.9 degrees. $180 would put us west, and then 190 would put us 190. All those would be acceptable ways. You don't need to do all of them. Questions on how we do that? We have data sections like that. How would we get acceleration then from force? This is one you should know. You should force equals mass times acceleration. That's one that you probably should know and not have to look up. But you're right. It is on your blue equation sheet. The force was 301 newtons. Mass is given to us. This is a bad way of doing it. Everybody watch up here. 301 divided by 165. Why is that bad? Yeah, I used the rounded answer I got before in order to round again, right? You don't want to round till the end, all right? So if you did something like I did here where I did that and then did another one, I didn't store that as a variable. You can go back to it by using second enter a few times, or you can just find it again. Okay, that's what I did, and then I took the square root of that. Now divide that number by 165. And notice in this case, it's probably not a big deal. It's 1.82, 1.83. But sometimes rounding multiple times throughout the problem is going to mess up the final answer. 1.83. What are the units for acceleration? Meters per second squared. Acceleration is scalar or a vector. Vector, therefore, needs direction. Yeah, it's the same direction as the force. Any questions on example 2? Example 3, again, adding vectors. We're still adding them algebraically now. This one's a little more complex, though. Notice we have 3 vectors this time. Man's walking 7.2 miles due west. He turns, walks 15 miles in another direction, comes again.